Greetings, it's Paul with the 25th and final introductory lecture for Math 117. The topic for today is, having sold a call option, how do you hedge it perfectly? You already know how to do this in the discrete case, and we're now going to do the same thing in the continuous case by using the Black-Scholes formula. So let's think about our call option. It's got a maturity date t, and it could get there in a single step, in two steps, in some finite number n of steps, or in accordance with the Wiener process that leads to the Black-Scholes formula. In any of these cases, the fair price at time 0 is e to the minus rt, that's the discounting, times the expectation of the share price at maturity time t minus the strike price, but that expectation is calculated only when the quantity in question is positive, and I can split that into two terms. In each term, I multiply by the indicator function of the interval from the strike price to infinity to make sure that we're only calculating for the case where the option is in the money. So we've got one term that involves the share price, we've got another term that involves the strike price, and they're both discounted. So what's the hedge? Well, if the option which we have sold is in the money, then we have to sell a share to the option holder for the strike price. It would be very nice just to have that share in hand on the maturity date, so that's part of the goal of our hedge. And if that happens, we are going to receive the strike price K. Therefore, any reasonable banker ought to be willing to lend us an amount of money that will not exceed the strike price K on the maturity date. If, on the other hand, the option is not in the money, then we want to try to end up with a hedging portfolio that consists of no shares and no remaining loan. As the stock price evolves, then, our hedging strategy is going to be to own some appropriate fraction of a share while having taken out a loan that will evolve to some fraction of the strike price. As the share price evolves, we'll either increase or decrease both the fraction of the share that we hold and the amount of money that we borrow. If the price is going up, we will buy more shares by taking out a larger loan. If the price is going down, we will sell off some of the shares that we own and use the proceeds to pay off part of our loan. Now let's introduce some notation for this. First, Deneen's notation, which I don't particularly like, and then my own rewrite. Deneen uses capital B of t to represent the amount e to the rt to which $1 will have grown in a bank account. And with that notation, I can write the Black-Scholes formula as saying the value of the option on time t is the share price at that time times a function of time, which I will call theta, minus e to the rt times a function which I will call beta. But here's a much better interpretation. If the option is exercised, you're going to receive the strike price from the option holder. And therefore, your banker will make you, let's call it a strike loan, whose balance will become K on the maturity date. At some time little t, the balance of such a loan will be the strike price discounted by e to the minus r times the time remaining until maturity. So, here is another rewrite of the Black-Scholes formula. The Black-Scholes formula is the share price at time t multiplied by a function called theta minus the discounted value of a loan that will evolve to equal the strike price multiplied by a function alpha, and alpha can now be interpreted as the fraction of the maximum amount that you can borrow that you have actually accepted. So, here's our hedging formula. We own a fraction of a share at time t, and its value is, of course, equal to the share price times the fraction of a share that we own. And we have taken out a loan, which, if alpha equals 1, will evolve till the strike price, but we've only taken out a fraction alpha of that amount. Now let's compare with the Black-Scholes formula, and noticing that our k sub t is precisely the strike price discounted by e to the minus r times the time left to go, we can interpret our theta and alpha in terms of functions you've already seen, which we have called g and h. G is the first messy thing that shows up in the Black-Scholes formula, and we now recognize that the normal distribution function evaluated for that g specifies the fraction of a share that we want to own. Furthermore, h is g minus a quantity that depends only on the volatility and the time. And comparing this with that, we see that the normal distribution function applied to h gives us the fraction of the maximum possible loan that we want to take out. N is a distribution function for a standard normal random variable, and therefore its values always lie between 0 and 1. We can interpret them, therefore, as probabilities. If you think back to how we derived the Black-Scholes formula, you realize that n applied to h is just the probability that the option will end up in the money, in which case we will receive the strike price from the option holder. And if we multiply that by k, we get the expected amount that we receive from the option holder. If we multiply by capital K sub t, that discounts the amount that we will receive from the option holder down to the current value of that amount. So we've now got a nice interpretation on the second term in the Black-Scholes formula. What about the first term? Well, we already have a nice interpretation of that as an expectation. It's the value of a contract that will give you one share on the maturity date, but only if the option turns out to be in the money, and then that has been discounted back to time t. Let's see if we can interpret it as a probability. Well, that has to be possible, because what does this mean? It's the probability that the standard normal random variable y has a value that's less than or equal to the value of g for arguments t and x sub t. You do a little bit of messy algebra, and you can convert this expression for the event into something that surprisingly is quite meaningful. Okay. So let's look at this term by term. Here is the price of the share at time little t. Here is the amount that it will evolve simply in accordance with standard interest. Here is the drift factor that is required for our volatility. These two things are both deterministic, the last term is not, the price also gets multiplied by a random amount, which is the exponential of our standard normal random variable, multiplied by the square root of t minus t in order to make its variance proportional to the elapsed time. And this has to be greater than or equal to the strike price multiplied by something that depends on the volatility and the time left. In other words, we can interpret the first term here as the probability that the final price will exceed some value that's a bit lower than the strike price. So now we've got three interpretations of the Black-Scholes formula. Looking at it term by term, we can interpret each term as something about our hedging portfolio. The first term involving the fraction of a share that we own, the second, the fraction of our maximum allowable loan that we have taken out, or we've just seen how to interpret each term as an expectation, or finally, as a probability. Unfortunately, none of these tell you how to design the hedging portfolio in the real world. So we need a fourth interpretation. In order to get that fourth interpretation, we have to go back to the Black-Scholes differential equation. Remember this? U is equal to the value of the option as a function of the time and the share price. And when you multiply that by R, it equals the derivative of the option value with respect to time plus R times the share value times the partial derivative of the option value with respect to the share price, plus another term that involves the volatility and involves the second derivative of the option value with respect to the share price. In doing the messy algebra, whereby we ascertained that when we plugged the Black-Scholes formula into this equation, it really turns out to be a solution, we discovered that the partial derivative with respect to the second argument was actually quite simple. It was just the standard normal distribution function with argument equal to the function that we've been calling g. And therefore, we have a formula for theta sub t, the fraction of a share we need to own. It's just the partial derivative of the option value with respect to the share price. And in fact, that's obvious, right? When we were doing this in the discrete case, the number of shares we wanted to hold was always given by theta equals delta v over delta x. The difference between the up and down option values and the ratio of the difference between the up and down option values to the difference between the up and down share prices. And in saying now that we have the partial derivative of the option value with respect to the share price, we've just taken the limit of that quantity. Can we do the same thing with the second term? Yes, indeed. If you recall, the Black-Scholes formula involves the share price and the strike price only as the logarithm of their ratio, or the difference of their logarithms. So differentiating with respect to one is going to behave very much like differentiating with respect to the other. And you can check for yourself if you take the Black-Scholes formula and differentiate it with respect to the strike price k. Initially you get three messy terms, but two of them cancel out, and you get a very simple result that the partial derivative of the option value with respect to the strike price is equal to the discounted value of the normal distribution function, not for g, but for h. That's wonderful. We now have a formula for alpha sub t. Take the partial of the option value with respect to the strike price and discount it. And I guess this is the way that the financial engineers who deal with derivatives actually try to design hedging portfolios. What they need to do is make numerical estimates of the partial derivative of the option value with respect to the share price and with respect to the strike price. I've written some Excel spreadsheets with which we can simulate hedging a call option, and there are two scenarios that are particularly simple to check out. First, I want to comment that I don't really understand this infinite product probability measure that we need here. It's mathematically a real mess, but who cares now? We can design for any omega in our sample space, that is, any evolution of the stock price with time, a hedging portfolio. And we're no longer mentioning probabilities. What's the price of a share on the maturity date? Well, it's a random variable. And remember how this works. It's the price at time 0 multiplied by e to the RT to take interest rates into account, multiplied by e to the minus sigma squared over 2t in order to make sure that this random variable is a martingale, multiplied by the exponential of a standard normal random variable multiplied by sigma square root of t in order to make its variance equal to sigma squared times t. The random variable y is as easy as can be. It's a standard normal random variable, expectation 0, variance 1. And of course, its probability density is greatest, think of the infamous bell curve, when the value is equal to 0. So we set y equal to 0 here, and we realize in that case the value at time t will be the value at time 0, increased in accordance with interest, but then decreased by the drift factor that we need to introduce in order to take into account that there's much more upside than downside in the random process. So if we choose that value as the strike price, then we know exactly the probability that the option will be in the money. The probability that will be in the money is precisely 1/2, and since that determines what fraction of our loan we take out, in this case we know that the initial loan we take out will be half the amount that will evolve to be worth the strike price after time capital T has elapsed. There's also another special case that we can check out, because we've got a formula for the number of shares that we have to hold in order to do our perfect hedge. That's determined by the function g, and if I set little t equal to 0, here is a formula for the function g. As before, this distribution function has a value of 0.5 when its argument is 0. In other words, a standard normal random variable is equally likely to be positive or negative. So we set the argument of the distribution function equal to 0. We exponentiate to solve for x0 over k, and we then do a little bit of algebra to get an equation for the strike price, move the k over there, move the exponential to the other side, and we see that if the strike price happens to be equal to the initial share price multiplied by e to the r plus sigma squared over 2 times the time to maturity, then our initial hedging portfolio will include precisely half a share. This is not intuitively obvious, in my opinion. The fact that when you derive the Black-Scholes formula, this very neat transformation from r minus sigma squared over 2 to r plus sigma squared over 2 happens is still black magic as far as I'm concerned. But this will mean we can do simulations in Excel where we know in advance that we start out with a hedging portfolio consisting precisely of half a share. So let's get busy in Excel and do some simulations. I'm done with this introduction.